Here's one more addendum. I realized that there's a very important prediction of relativity that I didn't talk about, and that is, why can't you go faster than light? I kind of built that into the axioms, that a material particle was supposed to be something whose trajectory in space-time was in a time-like direction, and that basically says you're not going faster than light. But why is that a physically reasonable postulate? Well, there's a simple reason for that, and that's basically that if you can travel faster than light, then you can go backwards in time. And so the real assumption that you can't go back is that you can't go backwards in time. Okay, now if you want to say, oh, I think you can, then you've got to deal with a host of weird paradoxes. So I'm going to assume this, which is maybe not absolutely rock solid, but it's about as solid as any assumption you can get. And we assume that the physics, this is why it's called relativity. Physics is the same for all observers, even if they're moving relative to each other. That's why it's called relativity. Okay, so that is a huge assumption, and now that we have the Lorentz transformations, it goes by the name of Lorentz invariance. Okay, and so it turns out that those two assumptions say you can't go faster than light, and I'm going to show you why. So here's what we know we can't do. So here's our standard picture of space-time. This assumption means that you can't take some particle or some piece of information and take it from here, let's say, to down here. Or you can't even take it over to, say, down here, because the t-coordinate is going in the wrong direction. Okay. But let's assume a little proof by contradiction, you can go faster than light. So you could make that material particle go to somewhere over here, for example. Well, I claim that combined with Lorentz invariance means you can actually set it up so that I can take this particle and have it end up here, okay, by using the aid of a couple of friends. So let me just redraw the picture. So what we're going to do is we're going to have this observer. He's going to pass that particle off to two friends in succession. One of the friends is going to be moving very fast. Let me draw a little light cone here. He's going to be moving very fast to the left, so his t prime axis is way over here, and his x prime axis is way over here. Okay, and he's going to take that particle, and he's going to definitely not go backwards in time according to him. He's going to have it end up somewhere, namely, he's going to have it end up, I'm going to express this as a vector, a little trajectory, right over here. And what you can see is that according to the x prime t prime grid, this is definitely on the positive t prime side of the x prime axis. But notice that is very much in the negative t direction according to the xt observer. Basically, we shouldn't be surprised by that. We know simultaneity is relative. We know that two things occurring at the same time is very much relative to an observer. And so what happened with the future and the past in terms of x prime, t prime being positive or negative, or t being positive or negative, is very much observer dependent. What's not observer dependent is the time cone, the future time cone and the past time cone. Those are not observer dependent. But with this assumption that we can actually go faster than light, we're sort of trying to say, well, maybe those time cones aren't really limitations. And what we're going to discover is they're the right limitations. Okay, so just to be really specific, let's say this ended up going backwards. Let's say this is B. Let's say it's 1 day. So this is, it looks like 1 day back in time according to the xt observer. And we'll see that it's, in a minute, we'll see that it's definitely not back in time for the x prime t prime observer. Okay. And let's say this A is 2 light days. So according to, oops, the dash would go here. Okay. And that's about 60 billion kilometers. So well past Pluto, but still not anything ridiculous by cosmic standards. Okay. And so according to this XT observer, this material particle that's been it passed off to this moving observer, he then shoots it off in this direction, and according to him, that's perfectly legal. It's in the T prime positive direction, and he hasn't really gone back in time in terms of T prime. But it definitely looks like you've gone back in time in terms of x and t. Now, you might think, well, what about the twin paradox? That there was these issues of you wanted to have a picture where two things kind of started together and ended together to make it really certain what's going on. Maybe just saying t is negative doesn't mean much because these two events are separated in space-time. Well, so then what we're going to do, actually, yeah, let me do the numbers here, and then I'll show you what we're going to do to make it really rock solid. Let's say that the velocity, the relative velocity, oops, I uncapped that for like 2 minutes or most. Okay, this is getting weak too, but oh well. The relative velocity, let's say, is my favorite √3/2, and so the gamma factor we've discovered is 2. The Lorentz transformation, if we get the signs right, he's actually going backwards. Actually, let's say this is negative from the pictures I had before. And if we get the signs right, the Lorentz transformation is gamma 1 minus v minus v1. That was about what Addendum 1 was about. And that turns out to be 2 plus √3, 2. And so, I'll squeeze it in up here. We get x prime t prime is 2 √3, 2 times, it's going 2 units over and 1 unit down. And so we get 4 minus √3 and then 2 √3 minus 2. The main thing is that this number here, the t prime, is positive. That's greater than 0. Okay. And so we've transformed this so that according to x prime, t prime is positive. Now, that's pretty obvious from the picture, but I wanted to make it a little more numerical. Okay. So now to really nail the thing down and not have to say, well, maybe this just is some coordinate fiction that doesn't really mean much, I want to actually get that particle to show up right here. So it's going to go one more day back. So these two things are both 1 day. And that's easy because that's just symmetrical. We just enlist one more observer. We pass off the particle to another guy who's going the opposite direction really, really quickly. So his t prime axis is like this. His x prime axis is like this. He's going at velocity plus √3/2 instead of minus √3/2. And according to him, this is still going forwards in time because here's his x prime axis and the t prime is on that side. So because he's going the other direction, this looks like the perfectly legal thing as well. So according to the red observer, this is just a particle that's moving faster than the speed of light, admitted, but not moving backwards in time. According to the blue observer, who he hands it off to, way out beyond the orbit of Pluto, this is a material particle. Yes, it's moving faster than the speed of light, but we're assuming that's legal. But he's not moving backwards in time according to the blue observer. But we get something that is absolutely, definitely, clearly moving backwards in time. It's, according to x and t, it's not moving at all. It showed up in exactly 2 days past, exactly where this guy was. So 2 days past on his own world line, this object shows up. And that's really, really, really moving backwards in time. It's inside the past time cone, and it's exactly backwards in time and not in space. And so that says that if you can enlist the aid of a couple of friends, and you believe in Lorentz invariance, you believe that the black, red, and blue descriptions of the world are all legal, none of them thought it was moving backwards in time. They just thought it was moving faster than the speed of light, and yet it really does end up moving backwards in time, according to the black observer, okay, when you do this. And so that's why, as long as you assume that moving backwards in time is not legal, then you can't move faster than the speed of light. Pretty relevant to the discussion of the neutrinos, these supposed faster-than-light neutrinos that was going on recently, which, of course, was bogus.